Good morning. In the chapter Work and Energy, we can look at the relation between force and potential energy and the stability analysis of the system. First, we can look at the relation between force and potential energy. If the force is a conservative force, it is the negative derivative of potential energy, f of x equal to minus du by dx, or we can write potential energy as the negative integral of the force. Then stability analysis of the system. The relation we have seen, f is equal to minus du by dx. It is not only used to calculate the force from potential energy but also used to analyze the stability of the system. How we can analyze using this equation? Take the example of one-dimensional harmonic oscillator. That is a simple harmonic oscillator or simple pendulum. The potential energy is given by u is equal to half kx square. When a graph is drawn between u and x, we get a parabola. U along the y-axis and x along the x-axis, we get a parabola. On the right of the origin, that is towards this side, the slope is positive. Slope positive means du by dx is positive. Hence, force is negative, which means force has a tendency to bring the particle towards the equilibrium position. This point is the equilibrium position. It implies that when the particle is displaced to positive x side, it experiences a negative force. That is, the particle has a tendency to come back to the equilibrium position. Similarly, on the left hand side, if it is displaced, the force has a tendency to come back to the equilibrium position. Here f is positive since du by dx is negative. Slope is negative here. So at the equilibrium point 0 or O, the slope of the graph is 0, means force is 0. That is the equilibrium. Here the force vanishes at the minimum point and the corresponding potential energy is minimum. It is called a stable equilibrium. Conditions for stable equilibrium. Example, for the case of a simple pendulum, du by dx equal to 0 and d square u by dx square is greater than 0. This is the condition for stable equilibrium. Now we can look at unstable equilibrium. If a pendulum is suspended from the roof like this and theta be the angle, at this point A, which is at a distance x from the bottom. At the bottom, we are considering potential energy to be 0. Potential energy at A is equal to mgx. But from the figure, this triangle, we can consider this triangle. Cos theta is equal to L minus x by x. By solving, we will get x equal to L into 1 minus cos theta. Substitute the value of x in the potential energy. U is equal to mgx. U is equal to mgl into 1 minus cos theta. Now take the derivative. U du by dx or du by d theta is equal to mgl sin theta. At equilibrium, du by d theta is equal to 0 and theta is equal to theta 0. 0 is equal to mgl sin theta 0 or sin theta 0 equal to 0 or pi. Plot a graph between u and theta. This is a graph between u and theta. It will be like this. This is the unstable equilibrium plot. Here at pi, du by d theta is equal to 0. It is an equilibrium point when du by d theta is equal to 0. But the corresponding potential energy is maximum. Here the potential energy is maximum, whereas in the case of stable equilibrium, potential energy was minimum. Here in the case of unstable equilibrium, du by d theta is equal to 0, but the potential energy is maximum. If it is in equilibrium or not, we will disturb the system from the equilibrium either towards the right or towards the left. Towards the right or left. But it does not come back to the equilibrium. If it is displaced here, it will go to this 2 pi position, that is u is equal to 0. It will not come back to the equilibrium position. Such an equilibrium is called unstable equilibrium. That is, this is the point of equilibrium, but if you are disturbing the particle, it will not come back to the equilibrium position. Such an equilibrium is called unstable equilibrium. On the right of theta 0 of the graph, slope is negative, so force is positive. On the left of theta equal to pi, the slope is positive, so the force is negative. In both the cases, the particle cannot come back to the equilibrium point. So it is an unstable equilibrium. Now the conditions for unstable equilibrium. We have seen the conditions for stable equilibrium. Now we can look at the condition for unstable equilibrium. du by dx equal to 0 and d square u by dx square less than 0, negative. In the earlier case it was positive, here it is negative. It is unstable equilibrium. Now the third equilibrium state is the neutral equilibrium. If d square u by d theta square or d square u by dx square is equal to 0, it is neither stable nor unstable, and all higher derivatives, that is d square d cube u by dx cube, d raised to 4 u by d x raised to 4, it can be taken as theta or x, more precisely x. So u is a constant in a region about x0. Such an equilibrium is called neutral equilibrium. First case is the stable equilibrium, that is du by dx equal to 0 and d square u by dx square positive. Second one is the du by dx equal to 0 and d square u by dx square negative. That is the unstable equilibrium. And the third one, neutral equilibrium, about x0 it is constant and all higher derivatives vanishes. Du by dx equal to 0 and d square u by dx square, d cube u by dx cube, etc. are 0, and it is called neutral equilibrium. This is the stability analysis of the system. Thank you.